principled design approach to scaffolding. Jay and Sue, y'all want to take it on?
Okay, now I'm unmuted. Sorry. My name is Jay Thomas, and I'll be presenting with my colleague Sue Ward about Hera, and I'm going to give a brief overview of our presentation. I'm going to talk about an overview of the extended evidence-centered design, or e-ECD model, and design science applied to learning. We're going to talk about what is Hera, the pilots and previous work, and our next steps with this learning tool. So, principled assessment design approaches all seek to clearly link claims about what test takers know and can do with observable behaviors like test answers, and include those concerns about validity claims from the very beginning. They take different approaches and may be thought more as heuristics than algorithmic approaches to validity. Theory of action, which is not listed in assessment design science from the bottom, have been used in ACT for several high-stakes assessment designs or redesigns because they consider the role of constraints early on in the process, which can prevent high-stakes testing programs from pursuing evidence types that cannot be part of the final design. Evidence-centered design, ECD, Mislevy's flavor of a principled assessment design approach, is the most well-known and was used by the College Board for the revisions of the AP courses, as well as the PISA and NAEP and TIMSS studies. PAD in general aims to make the logic and validity arguments explicit and efficient. How do we link cognition, observation, and claims of the assessment triangle from knowing what students know? PAD approaches help to make articulation of the claims in the argument chain explicit, and the accumulation of evidence to support the claims a procedural byproduct of the design process. The ultimate goal is to identify and minimize any construct or relevant variance so that tasks and task models give stronger evidence for claims about what students know and can do, because that's our goal in assessment, is to know exactly what the students know and can do. So, in addition to the validity arguments discussed previously, there's a strong utility component for having a PAD approach to designing assessments, whether they be formative or summative, especially that they formalize item writer thought processes and routines, and that they produce efficiencies and cost savings. These processes assist in AIG, or automatic item generation, and have been used in Mislevy's PADI system for automated test assembly, which uses the documentation of ECD to facilitate test assembly. But why would we pick science for a learning tool to apply this principled design approach? Well, the next generation science standards and the NRC framework for science education changed the idea of what scientific literacy really means and how it should be taught and assessed. Science standards are no longer a list of factoids that students memorize and regurgitate as they were in the 80s and 90s. They strive to have students engage in scientific sense-making of real phenomena, using 3 strands or facets, as shown in the diagram on the left. Science practices are what scientists, and therefore students as well, do. These include constructs like interpreting data, engaging in arguments from evidence, and scientific investigation skills. Cross-cutting concepts in science are how scientists and students think, such as using patterns and cause and effect reasoning, as we heard in a lecture earlier. And finally, disciplinary core ideas represent the scientific content that students are trying to understand and make sense of. The idea is that scientifically literate students will become scientifically literate adults who can apply scientific content knowledge and practices to any situation in their lives or community. You must have all 3 strands woven together. Content knowledge is simply not enough. One of the big changes from previous science standards, particularly NSES, is that science practices and cross-cutting concepts are interwoven into every concept and every unit. There's no longer that first chapter of the textbook where you learn about scientific practices and then it's all forgotten. But this raises major issues for traditionally underserved learners. They are far more likely to not have access to opportunity to learn advanced topics like chemistry and physics. BIPOC students and students in high poverty schools are more likely not have qualified teachers for those subjects. They're also less likely to have access to properly equipped labs and supplies. So the decision was made to apply a principled assessment design approach to science using computer simulations as a way to introduce and explore scientific phenomena for all students, regardless of the lab space, time, and money available to them in their traditional classroom. The National Academy's report on assessing the NGSS suggests that using technologies such as simulations to better assess the depth and breadth of NGSS will be necessary. So Hera uses simulations for formative assessment. Hera is built on the idea of learning progressions, and learning progressions are hypothesized descriptions of learning based upon existing and ongoing research in cognition and pedagogy that move learners from their intuitive conception or lower anchor where they begin to one or more stepping stones or intermediate anchors towards a clearly defined big idea in science or upper anchor. They are not developmentally inevitable, but they may be developmentally constrained. And these are not fixed linear paths. There are stops and starts, and different students will take different paths. But in general, with instruction, most students will move along the progression. And there's been a lot written about the students in the group described by Gottwals and Songer as the messy middle that make a variety of mistakes, sometimes applying their new knowledge, skills, and abilities, their KSAs, correctly, and sometimes reverting to earlier stages. By framing these skills along a progression, specific skills and their immediate proximal precursors and their distant multiple step precursors, a scaffolding approach to assist learning and guide instruction can be used. And one simplified structure of the learning progression of the skill for interpolation and extrapolation is shown here on the screen. So here's the extended ECD model. So it isn't just enough to have the KSA model of what skills the student possesses. We need a model for how students' KSAs change as they learn, because ECD is based on the idea that you are measuring KSAs at a specific point in time. They shouldn't change during the test. But what we're doing is we're trying to move those students along the learning progression. So we also need a model that explains what evidence is needed to justify claims about changes in the students' KSAs as they work. And finally, we don't need task models that describe the facets of a particular item, but also a model that will explain how we can scaffold those items when a student is unable to perform a skill. We need task supports for both the KSA tested as well as the precursor KSAs. In a perfect world, we would be able to use some sort of multidimensional IRT to combine information from dozens or hundreds of items to get a better picture of exactly what skills along the progressions the student has mastery, partial mastery, or no mastery of. We may eventually be able to discover links to precursor skills or enhancing skills that were not in the initial theoretical learning progressions. But what did that lead us to? And that led us to Hera as an instructional model. And at this point, I'm going to turn it over to Sue.
Thanks, Jay. I'll be describing an application of e-ECD called Hera, and then I'll turn it back over to Jay to talk about our current status and next steps. Hera stands for Holistic Educational Resources and Assessment. It is an adaptive learning system designed to complement science curricula by helping students build scientific reasoning skills. ACT has developed 14 lessons for 2 separate pilots, and each lesson is designed to take approximately 30 to 40 minutes to complete. Lessons can be completed as a classroom activity or by students independently. The goal of Hera is to synergize assessment and learning by engaging students in NGSS science practices. So how are lessons structured? Generally speaking, a Hera lesson is comprised of a brief introduction, a simulation activity, and 10 learning scaffolded items. The introduction presents images and phenomena related to the topic to elicit curiosity and set the stage for learning. Here we see examples from lessons about energy and wavelengths. Let's take a closer look at the various parts of a lesson. After the introduction, the student is presented with a computer-based simulation with 3 purposes. First, to build familiarity with the topic and the related terminology, concepts, and measurement units. Second, to enact learning by doing, which gives the student a sense of control through the ability to make choices. And third, to provide an opportunity to observe and collect data as the student would in a lab. This strategy elicits intrinsic motivation and contributes to an overall understanding of the concept. Thus, the simulation provides a starting point for learning. Here, we see a simulation that allows the student to experiment with variables of temperature and pressure. Hera uses learning scaffolded items to help the student successfully solve problems based on the simulation in a progression of increasing difficulty and complexity. The idea is assessment first, learning next. Students have 2 chances to answer each item correctly. The scaffolds are offered only if the student submits an incorrect response on the first attempt. When the student selects a scaffold, a pop-up box appears with additional text and visual cues to support learning. In Hera lessons, there are 3 levels of scaffolds: rephrase, break it down, and teach me. Each level provides a different strategy to help students replicate the scientific reasoning they need to arrive at a correct response for themselves on the second attempt. Hera uses gamification to optimize motivation. Scaffolds must be purchased from a limited bank of coins. Points are earned based on correct answers, and badges are awarded based on the final point total. One of the primary additions for the second pilot was the confidence component. With every response attempt, the learner records their confidence level. At the end of the lesson, the learner also reports their confidence overall, as well as their perceived science ability or self-efficacy. This feedback provides information about real-time metacognition and changes in confidence from the beginning to the end of the lesson. We also incorporated performance tasks into some of the lessons for the second pilot. This type of authentic task serves to demonstrate essential skills such as critical thinking and scientific reasoning, in addition to mastery of the content. Performance tasks follow the same structure as the main lesson, using a simulation to answer questions, but do not provide access to scaffolds and do not provide real-time feedback. Our first study using the Hera model involved a large pilot in 2018 that examined how the 3 types of learning supports would be used by real learners. We designed 6 lessons at the high school level on the Smart Sparrow platform as a proof of concept. The screenshot at the top shows how a question appeared in this format. We then launched the lessons on Amazon's Mechanical Turk environment, and 2,775 participants accepted the tasks. The results confirmed that reliability of the first attempt with learning scaffolded items is equivalent to typical assessment data. As shown in the chart on the bottom right, we looked at the use of scaffolds under different conditions. Remember the limited bank of coins? When the scaffolds were available without any cost and before the first attempt, students used more help. When the scaffolds were available only if purchased, especially if break it down and teach me cost more, students tended to be more selective about using the scaffolds. So with this knowledge, we retained all 3 levels of scaffolds offered after the first attempt and at varying costs for the second phase of the project. For our second study in 2020, we redesigned the system with the help of a vendor, and we created 8 new lessons designed for middle school students on a custom instance of OpenEdX, which is the open source version of the software running the edX platform. The redesign introduced a variety of new features, including formalizing the leveled scaffolds and the varying cost structures, adding the confidence reporting feature, and improving navigation with the dashboard you see here. We tested it out in 4 middle school classrooms, totaling nearly 200 participants. Although the pilot was limited due to COVID, we were able to collect information on student confidence levels in conjunction with the learning scaffolded items and gamification choices made throughout the lesson. The Hera project was put on hold in the fall of 2020 due to limited resources. However, we recently restarted the OpenEdX system, and we are hoping to conduct additional research and potentially expand the system for delivery to high school students using ACT technology. I'll turn it back over to Jay to talk about our status and next steps.
So in this era of digital learning, one of the things that we wanted to make certain was that users found the materials engaging. And we found that for both the adults in Mechanical Turk and for the students in the COVID pilot, that they found the materials engaging. We also found that the technical aspects worked well, which was really important to us, as we know that there have been lots of problems with all sorts of online usage. The learning support usage was approximately what we figured it would be, particularly with the second phase. And the target students' results were very promising during the COVID trial. We've already published on our e-ECD model, and we're making some conference presentations, and it's the subject of an upcoming book chapter being written by Tom Langenfeld and Alina von Davier. The next step for us is to really try and publish these findings so that people can begin to produce better and better learning tools, particularly that are NGSS aligned, and applying what we learned to other learning and gamification projects. Right now, we're working internally to secure funding for a larger scale study targeting individual students in classrooms next school year, because we want to really look at how if this can help to narrow the performance gap between traditionally underserved learners and white and Asian students, and looking at how the different gamification elements work effectively. So at this point, I will turn it over to questions.